Hello everyone, my name is Hailun. I'm a third-year PhD student from Rutgers University, and today I'm very happy to be here to present our work, the case for learned provenance graph storage systems. Attack investigation is very important for understanding existing attacks as well as defending against future attacks. Given the attack clue, attack investigation can get a big picture of the attack by tracing the attack sources as well as the attack impacts. Usually, attack investigation uses system logs for analysis. However, the logs can be very large and hard to understand. So existing work also tries to convert the log into a provenance graph. And in this provenance graph, the loads are the system subjects or objects such as a process or a file. And the edges are the system activities such as a read or write operation. So given the attack clue as a start point, backward tracing from it can find the root cause of the attack, and forward searching from it can understand the attack damages. However, even though provenance graph brings so many benefits, such as simplifying the log analysis, in practice, storing and analyzing the provenance graph could be very challenging. On the one hand, the system behaviors could be very complicated, which makes the graph size inevitably become large. For example, a very simple system behavior such as using the Firefox to open a website can issue thousands of the syscalls, which brings thousands of the new edges and nodes to the provenance graph. On the other hand, the recent advanced attacks requires the system to store the large provenance graph for a very long time. For example, as shown by existing report, the attack can exist in the system for 8 months or even years without being noticed. So storing a large provenance graph for such a long time can bring high storage overhead. To efficiently evaluate, manage, and store the provenance graph, existing work use databases. For example, the relational databases store the provenance graph as a vertex table and an edge table. The nodes and the edges in this provenance graph are flattened into individual recalls. And when investigating the attack, the relational databases will iteratively join these two tables and search them to find the final result. But as we can see, the relational databases are not storage efficient because they store the original provenance graph, which can contain much redundancy. And for example, the word file in the vertex table has been stored for twice. Also, relational databases is not query efficient because when querying the graph, they need to iteratively query these two tables to get the final result, which can bring high I/O overhead. Another kind of databases are graph databases, which are more suitable for graph data storage. Given the provenance graph, the graph databases store the graph data itself as well as the graph structure. And when investigating the attack, the graph databases directly perform the investigation on the graph. However, it's still not storage efficient because still, the graph databases store the original provenance graph, which can contain much redundancy. And also, the graph databases are not query efficient because the graph data could be very large, and it's almost impossible for us to load them into the memory. So querying on such a large provenance graph can still introduce high I/O overhead. So motivated by these challenges, we propose our solution. We want to use the deep neural network model as a database for provenance data. And more specifically, we are inspired by the fact that a small deep neural network model can actually memorize a very large dataset, as shown in this table. We also find that provenance graph data is highly structured data, which is very similar to the natural language data. And such data can be easily learned by the existing models. So we felt that using a very small model, maybe we can memorize a very large provenance graph. We also find that deep neural network literally suppose data queries. So when storing the provenance graph and when storing a record, taking the token of this record as the input, the deep neural network model will try to memorize the subsequent characters by training on the next character prediction task. And when we want to recover the record, given the token of this record as the input to the model will try to predict the following characters and recover the original record. So Based on all of this, we felt that using a deep neural network model as a database is practical. Also, if we can use the deep neural network model as a database, it brings many benefits. For example, we can achieve the storage effectiveness because in the best case, a very large graph can be replaced by a very small model. We can also make the query more efficient. As we mentioned before, the deep neural network literally supports necessary queries. Also, the small models make it impossible to manage the data in the memory. And next, I will elaborate each step of our design to discuss how we implement such a database. Given the provenance graph, we first flatten it into individual records, just like relational databases. And such preprocessing helps us to convert the storage task into a natural language processing task and make the model training possible. Then we perform the redundancy reduction. More specifically, we perform the values, the words, the case reduction. And for the values such as the timestamp, we replace them with the offsets between it and the minimal one. For example, this timestamp is replaced by the number 5, which is the offset between the original timestamp 155 and the minimum timestamp 150. And for the words, we count the frequency of words and sort the words based on their frequencies. Then we replace the most frequent word with the shortest numerical code. And in that case, we detect that the word read is the most frequent word in the provenance graph. So we replace them with the shortest code 1. We also find the combinations of case are enumerable, which means that we can replace the case of the records with some template ID. For example, in that example, we replace the case of this record with the template ID 1. Then we convert the text representation to the numerical representation for the model training by using character to vector. We also perform the indexing. For the node, the index of the node is the ID of the node. And for edges, the index of an edge is the ID of the edge as well as the IDs of the source and destination nodes. Then using these indexes as the tokens and the inputs to the deep neural network model, we can train the deep neural network model on the next character prediction task to memorize the provenance graph. And during this process, deep neural network can make mispredictions, and we just record these mispredictions in a calibration table. So when querying the provenance graph, given the attack clue as a start point, we first search the indexes to find all the IDs of the expected vertices and edges, and then we use the IDs as the input to the model, and the model will try to recover the details of the records. And during this process, mispredictions will be calibrated by the calibration table. Then we convert the numerical representation back to the text representation by checking the reference table, and finally return the query result. We evaluate our system on 12 datasets as well as the corresponding provenance graphs. We also compare our system with a graph database Neo4j, a relational database Quickstep, and compress the Quickstep, as well as the databases with our preprocessing reduction rules. In terms of the storage efficiency results, we find that our system could be 26 times, 17 times, and 5 times smaller than the existing system. And when we comparing the query efficiency, we find that our system could be 2 times faster than the existing system. However, when we compare the time we used to build this database, we find that our system can be much slower, so very unfortunately. But for that case, it's kind of acceptable because provenance data storage is kind of a cold storage problem. So we only need to write the provenance data into the system once. But for more general tasks and more general data, it could be a problem. Our code and paper are now available. And if you are interested and want to know more details, please scan the QR code. Thank you.